let's see some examples of how to use this Dirac Delta function. Remember, we said that it comes as a spike, right, which is basically nothing but whenever you take derivative of something which is changing in amplitude instantaneously, then it results in the Dirac Delta function. Now let's take the derivative of this rectangular function. So how does this rectangular function look like? This magnitude is a, this is half, this is plus half. So this is a rect of t. Now it's plot its derivative. The derivative in this portion is 0, and in this portion also it is 0 because it's all constant, and in this portion where it is 1 or it is plus a is also 0. So the only point where the derivative is non-zero is at minus half and plus half. Clearly, what happens at minus half? The signal suddenly jumps in magnitude. Basically, it increases. Because it increases, you get a Dirac Delta function in the positive direction. And at plus half, what happens? The signal suddenly decreases. So the slope has to be negative. So you get a negative Dirac Delta function. Great. Now, what is the area? So as you can see here, the signal went to plus a from 0. Okay, which means this area here has to be plus a, and this area here has to be minus a. Remember, for step function it went from 0 to 1 and hence the area was 1, but here it's going from 0 to plus a, so the area has to be plus a here. Okay. All right, now let's go to our standard signal which we have been using often for various exercises. This is minus 1, this is plus 1, and this is 1. Now let's take the derivative of this signal with respect to time. So what do you think happens till minus 1? It is 0, clearly has to be 0. After 1 also it is 0, great. Now what happens from minus 1 to 0? From minus 1 to 0, there is a straight line at a fixed slope, right? So which means the slope is a constant from minus 1 to 0. So you will get something like this. Okay. All right. At 0, what happens? The signal becomes constant from 0 to 1. Okay, which means the slope now changes to 0. Okay, so things are continuous, there is no sudden jump, so everything has been smoothly increasing. So we say that from 0 to 1, the signal slope is 0. But what happens at 1? At 1, there is a sudden fall from 1 to 0. At time instant 1, there is a sudden fall in amplitude from 1 to 0. So which means there is a spike in the derivative, and in what direction? It has to be negative because signal has decreased. So there is a Dirac Delta function here. And what is the area of the Dirac Delta function? Because it is plus 1 there and it has reduced to 0, this will be minus 1. So this is the derivative of the signal that we are looking for. Okay. Now let's say somebody asks you to integrate this. Now let's say we take the spike and then feed it to another circuit which has integrative properties like that of an inductor. And what do you get out of that inductor? So let's see what happens. So basically you are integrating the Dirac Delta function, the spike, from minus infinity to t. What does this mean? So it means that till t is equal to 0, you have area to be 0, there is nothing. at t is equal to 0, you are now computing the area of the Dirac delta function. Okay. So from t is equal to 0, the area starts increasing. Till that point, the area is 0. So the integration from minus infinity to t, where t is less than 0, the area under this curve is nothing, it is 0. Now what happens when you try to compute the area for values greater than t, greater than 0? Then in that case, you are trying to compute the area of the signal which is present in this interval, in this region. So which means you are including the area that is present under the Dirac delta function. The moment you include the Dirac delta function, the area jumps to 1, right? So remember that from minus infinity to some epsilon which is greater than 0. So let us call that this is epsilon. The Dirac delta function, if you try to compute the area, it is going to be 1. In other words, this is almost like at t equal to 0. So if you compute, let's call this as some r of t or some b of t dt. Okay, maybe let's avoid confusion and call this as tau. From minus infinity to t. So this epsilon is so small that as long as t's value is negative, this integration is going to be 0, because the area, there is no signal here, signal is basically 0, right? The moment t is going to be greater than 0, so if t here is greater than 0, then you can split this integral into epsilon minus infinity to minus epsilon plus minus epsilon to epsilon plus epsilon to t, right? So this portion will be 0, this portion will also be 0, whereas we have a portion here which gives you 1. So no matter what the value of t is, as long as t is positive, this integral's value will be always equal to 1, or the area that is present for the Dirac delta function. So this is in fact going to look like 0 till t equal to 0. After that, it will be 1, which is basically our step function, right? We obtain the Dirac delta function as the derivative of the step function. So in order to obtain step function from the Dirac delta function, all we had to do was integral, right? So that makes sense, and that's exactly what is happening here. So if you integrate the Dirac delta function, you get the step function. So now let's see what happens if you integrate these outputs that we got earlier. So if you integrate them, remember the first Dirac delta, if you integrate it, starts at minus half, so it needs to have a step function like this. The second one, it starts at plus half and it will have a magnitude minus a. So you need to sum them up both. So when you sum up, so at this point, here plus a, here minus a gets cancelled. So we'll have the rectangular function back. Okay, and similarly, when you integrate this function, what do you have? So you have till minus 1 0, and then after minus 1 the area starts increasing, right? Basically you compute the area in this area and then you compute this area and so on. So the area keeps increasing. The area at 0 is basically the total area present here, which is 1 times 1, which is 1, that is what you got here. And then the area remains constant after that. So from minus 1 till whatever this point, so the area in this region is still equal to the area which was present between -1 and 0. So it's all the same till you reach +1. And after you reach +1, remember this is a step function in the negative direction. So you just add with a step function like this. So that will cancel out these two and we would get back our original signal. Alright, so which gives us the original signal back. So this way we now know how to take the derivatives of sudden jumps, which will give us Dirac Delta functions, and how to integrate these Dirac Delta function to get back our original functions. So this gives us a very nice model of how to work with spikes in real life and how you can actually get the real signal back. Okay. Let's see some more examples. Now we already saw what happens to a rectangular function when you take its derivative. What if you have a periodic rectangular function? This is a periodic rectangular function with period 3/2. So here capital T is 3/2. Alright, now what happens when you take the derivative? Same thing, you get a periodic signal once again, but now whenever there is an increase, there is a positive impulse. Whenever there is a decrease, there is a negative impulse. So this is 1, -1. And so this repeats. Okay. Now, how would you plot this function? So this is as good as saying that you are multiplying x of t with delta of t minus nt. Essentially, you are constructing a periodic signal out of the Dirac Delta functions. So this is what we will call as an impulse train. Why is this called an impulse train? It will become clear when you see the plot. So at n is equal to 0, you get the Dirac Delta function here. At t is equal to 0, and let's say t is equal to 2t, 3t, so on, and minus t, minus 2t, minus 3. So at n is equal to 1, you get a Dirac Delta function here. At n is equal to 2, you get another Dirac Delta function here, and so on. So basically what we have here is a periodic signal, and in each period we have a Dirac Delta function. And then it keeps repeating forever infinitely. So this is what is called as an impulse train. It's a train where you constantly see impulse functions or the Dirac Delta functions. Now if you multiply some x of t with this, okay, how does it look like? Or let's say, how does that look like? This is x of t. Now when you multiply these two, remember what happens when you multiply a function with a Dirac Delta function? You just get the Dirac Delta function back, but with the scaled value of whatever is the value of the function at that particular point. So in other words, so you get this back at minus 3t, but the area now is x of minus 3t. Get this back here. Area is x of minus 2t. And at this point, it is x of minus t. And at this point, as you can see, it goes in the negative direction. It is x of t. And here, it is x of 2t. And here, it is x of 3t. So you get the envelope of the signal as such, and the Dirac delta functions get scaled by the instantaneous values of the signal at those points. So this is almost like discretizing a continuous time signal. So converting a continuous time signal to a discrete time signal can be mathematically represented or modeled using product of that signal with an impulse train. So this is where the discretization is captured using an impulse train model. So the impulse train becomes very useful in this scenario where you want to convert an analog signal to a digital signal. So the ADCs are typically modeled using this expression, okay, where an analog continuous time signal is converted to a digital discrete time signal. So this becomes very useful in their analysis. So in this course, we will not do analysis of ADCs. You will keep using this model. So it is good to know how this model was designed and why it is designed.